Dear ladies and gentlemen, students and postgraduates, my name is Vladimir Zhmur. I am a professor of the Moscow Institute of Physics and Technology, specializing in continuum mechanics. The purpose of the present report is to talk about shock waves, why and how they are formed, what physical properties of the medium are necessary for the existence of shock waves, how to describe shock waves in simplest way, to present the basic ratios for shock waves in the air. What does weak or strong shock waves mean? And finally, I will introduce you to the problem of strong explosions. Shock waves, strong pressure waves in any elastic medium such as air, water, or a solid substance. Shock waves are produced by supersonic aircraft, explosions, lightning, or other phenomena that create violent changes in pressure. Shock waves differ from sound waves in that the wave front in that compression take place is a region of sudden and violent changes in stress, density, or temperature. Because of this, shock waves propagate in a manner different from that of ordinary acoustic waves. In particular, shock waves travel faster than sound, and their speed increases as the amplitude is raised. But the intensity of shock waves also decreases faster than does that of the sound wave, because some of the energy of shock waves is expended to heat the medium in which it travels. The amplitude of a strong wave, as created in air by explosion, decreases almost as the inverse square of the distance until the wave has become so weak that it obeys the laws of acoustic waves. Shock waves change the mechanical, electrical, and thermal properties of the compressible material. Let's look at some pictures. The first one shows the qualitative structure of the shock waves. The most important part of the shock wave is a shock wave front. You can see it here. The thickness of front is negligible. Therefore, it is assumed that all the parameters of the medium are discontinuous at the shock wave's front. The front itself moves through the particles of the medium at supersonic speed. Behind the front is a layer of compressed gas. This is compressed area. Then the discharge zone, decompressed phase. Decompressed phase is here. We will mainly interested in the shock wave front and characteristics of the medium before and after the front. The following figures shows examples of shock waves behind a sharp cone. You can see it here. This is shock waves here and here. This is shadow pattern of flow around sharp cone in the air. Mach number is some more than 2. Reynolds number more than 1 million. Shadow pattern of supersonic flow around the planted body. You can see shock waves here. In this picture, transonic flow around the aircraft, a fog skirt. This phenomenon is very often confused with the formation of shock waves. Here you can see a picture of shock waves from an airplane model in air tube and from 2 airplanes in real conditions. This is model in air tube, and this is the picture of supersonic flows around the aircrafts. Let's move on the description of shock waves. In this figure shows a picture of passage of shock waves over time through a fixed point in space. The shock wave front is a very narrow layer in which the parameters of the medium change almost abruptly from the values before the jump and the values after the jump. Let's try to explain the physical reasons for the formation of narrow transition zone at a jump. Physical causes of shock waves occurrence. The velocity of disturbance depends on the magnitude of the disturbance. The greater the disturbance, the higher the speed. This is how an area with a large gradient of environmental property is formed. In the area with large gradient properties, in general, friction and diffusion can be neglected. As an example, let's consider the simplex nonlinear equation demonstrating the role of nonlinearity in propagation of perturbation. This part of these equations is similar to the same part of real equations for gas or for water. Consider evolution of a smooth pressure or density step over time. In a figure, the vertical axis is pressure. It's here, pressure or density, here, and so on. The horizontal axis is the distance in the direction of movement of disturbance. Over time, the thickness of a gradient zone decreases, and there is a point in time then viscosity of a higher derivative cannot be neglected. You can see this friction is maybe neglected, friction is negligible, but in this picture friction is very important. But if we consider the more time than this one, you can get impossible situation for the pressure. When in the point there were three meaning of the pressure or three meaning of density, it's impossible. So we cannot pass to this picture. We understand that friction is very important only in the case of a very narrow friction zone. More realistic nonlinear equations with viscosity is the Burger's equation. You can see this one. It's a Burger's equation. Here is nonlinearity and viscosity. Both phenomena are present in this equation. And we consider the solution with boundary conditions when u tends to one constant and u tends to different constants for different kind of infinity, in plus infinity or minus infinity. Let's find a solution of Burger's equations moving to the right with a constant velocity u and constant waveform. Let's switch to the movable coordinate system. You can see this x is a movable x, but this one is not movable. In this case, the solution and equation leads to the different, more simple form. It's a usual differential equation. This equation can be solved very easy. This is the salvation of this equation, and this is the velocity of moving of this wave. This is a picture, shows the main properties of this solution. we see that in minus infinity or in plus infinity, it leads to the constants, and there is a gradient zone. This is a gradient zone. The thickness of a gradient zone depends on a parameter of viscosity. This viscosity parameter, this one. The width of the gradient zone at low viscosity parameter, so weak viscosity, is exponentially small. In the limit at this coefficient leads to 0, we get a step. This is a shock wave. You can see it here. This is shock wave, and this is velocity propagation of this wave in the case of very small coefficient of viscosity. The propagation viscosity of such waves doesn't depend on the viscosity and width of the gradient zone. The idea of shock waves describing, without taking into account diffusion, viscosity, and thermal conductivity, determine the relationship between the parameters of the medium before and after the jump, and find the speed of movement of this jump itself. Note, since jump have appeared, differential conservation laws cannot be used, but integral conservation laws are valid. For example, let us consider the laws of mass conservation. You can see here two different types of these laws. The first one is integral law of mass conservation. This is here. And here is jumps of density are possible. In the differential form of equation or law of mass conservation, jumps of density are not possible. So, for shock waves, we have to use the integral laws of conservations. Let us consider one-dimensional case and the tube in which there is gas with shock waves inside of this gas moving to right. S plus is a position of shock wave front before the front, S minus the same point after the shock. U is the speed of movement of this shock wave, and if we choose two different coordinate x1 and x2 in this tube and consider the mass between these 2 points, we can write the law for mass conservation in this case. So this is mass between 2 points, and this is mass flux incoming and outcoming from this zone. This differential equation is very simple. We can divide the distance between x1 and x2 by 2 parts. The first part is from x2 to the position of the shock waves, and the second part is the distance between shock wave and x1. In this case, we can divide this integral by 2 parts, and after this simple consideration, we obtain condition at the jump. Here is this condition. U is the velocity of shock wave. The square brackets means the difference between parameters before shock waves and after shock waves. In this case, it's density jump. This one is mass flux jump. So, in this equation, we describe all parameters together: velocity, density jump, and flux jump. It's very interesting to compare differential form of laws, and this one is differential form of mass conservation law. And this is the consequence of integral law. Knowing the conservation law, the differential conservation law, we can write a jump condition for this law. To do this, the differential form of the law, we need to replace the time derivative of the considered value with a jump of this value multiplied by the speed of the jump with a minus sign. At the same time, replace the space derivative of the flow of the considered characteristics with a jump of this flow at points of rupture. Now consider a gas dynamics. For gas dynamics, we use three laws of conservation. The first one is conservation of mass. The second one, conservation of momentum. And the third one is energy conservation. We have three equations to solve this problem. We have introduced thermal energy is here, its kinetic energy is thermal energy, and this is energy flux. This is momentum, this is flux of momentum, and this is density, and this is flux of mass. Let's consider thought speed and entropy. They will necessary for us in nearest future. The consequence from the integral conservation laws from these equations, you can see here. We have three analog of these conservation laws on a jump. Let us consider the shock waves. This is shock waves front. As a rule, we know pre-jump environmental parameters such as density, speed of movement of particles, and the pressure. The speed of movement of shock waves we don't know, but we want to find it. And unknown post-jump environment parameters, density, velocity, and pressure. So we want to know this parameter if you know this one. Also, we want to determine the velocity of propagation of shock wave. But we have to know the intensity of shock waves. So if you know pressure after the shock wave, we know intensity of these shock waves. Solving these equations to determine of all of these three parameters, rho, u, and this u, we obtain so-called Gauguin rations. This is Gauguin rations. It describes the parameter after shock waves, if you know parameter before shock waves. So it's the velocity of particle propagation. This is density after the shock, and this is sound velocity after the shock. And this is the movement of shock waves itself. Conclusions from these Gauguin rations. The environment parameters, density, velocity of particles, and pressure, including the entropy and sound speed, increase after the passage of the shock wave. So P2 is more than P1, ρ2 is more than ρ1, and so on. The speed of shock wave is greater than sound speed of the undisturbed medium. So Mach number is more than unity. With unlimited increase of the intensity parameter of intensity of shock waves, all parameters of the medium except density grow indefinitely. Let's consider weak shock waves. In this case, the intensity of shock waves is small. Z is very small. Decomposing Hugoniot ratios into power series by Z up to including the third power, we obtain the relations. This is the first power of intensity here, here, and here. This is square power of this parameter, and this is the third power of this parameter. For shock waves with acceptable accuracy, we can assume that entropy is conserved, this equation. For strong waves, we have Z much more than unity. In this case, the propagation of shock waves is more than particles movement in an undisturbed area, and Mach number is more than unity. But the conditions on front of the shock waves is very simple. Here is speed of movement of the shock wave in two formulas for speed of movement of particles and for pressure. And in this case, limited density difference for ρ2 divided by ρ1 approximately is equal to 6. Conclusions from strong shock waves conditions. In the problem of a strong explosions of all parameters of undisturbed medium, we need to know the density ρ1 only. And now we consider this strong explosion problem. The physical formulation of the problem. In the unlimited space with ideal gas of density ρ sub 0, at the initial moment of time t equal to 0, a strong explosion of the energy E took place. A strong waves was formed with centrally symmetrically propagates from the explosion point according to the some unknown law. We need to determine the dependence of radius of this zone on time. Now this problem in the picture. This is the point of explosions. This is the radius of shock waves zone for the time t. This is density of undisturbed media. This is energy of explosion, and the connection between propagation of shock waves and radius, you can see here. The time derivative of r is equal to u. The condition on the jump, we have gotten it on the previous slides. It's three conditions. It's conditions for movement of particles after shock wave. This is density after shock waves. This is pressure after shock wave. And this is propagation of shock, speed of propagation of shock wave. For this problem, we have three task parameters: energy, density of undisturbed media, and time. Let us use dimensions to solve this problem. The dimensions of energy, density, and t are well known. And if we divide by energy by density, we have two dimensions, time and distance, and there is no dimensions of mass. And we have time from 3 dimensions, energy, density, and t. It's impossible to make dimensionless number. From another hand, the distance, this distance, depends on this parameter, energy, density, and t. Length dimensions from these 3 parameters is very simple to get. You can see it here, and time in this formula is in this power 2 by 5. And non-dimensional distance r is r from t divided by this parameter, is non-dimensional size for this problem. According to P theorem, non-dimensional r must be a non-dimensional function that depends on non-dimensional parameters which composed of parameters of the problem, rho, e, and t. But from rho, e, and t, you cannot produce a non-dimensional number. Hence, f is constant. In the result, we obtain very simple conclusions. Non-dimensional distance is constant. So, the law of shock wave propagation in strong explosion is described by very simple equation. You can see this equation here, and time dependence of this distance. But this non-dimensional parameter k cannot be obtained from the theory of dimensions. You understood that we didn't use the theory, the gas dynamics. We use dimension theory only. American scientist Jeffrey Taylor used the movie about demonstrating the atomic bomb explosion power in the United States at the end of World War II to calculate the energy of this bomb. But it was a top secret of the United States. And to understand and to solve and to find this top secret parameter, we need no dimensions only. This is Jeffrey Taylor, and this academician Leonid Sedov is Russian academician which solve the same problem. This information about Taylor, this information about Sedov. Let's introduce in self-similar Taylor solution of strong explosion problem in zone between point of explosion and the position of shock wave in time of t. The shock wave is at nonlinear distance is equal 0. You can see here it's nonlinear distance in the zone of explosion. And from condition of jump, we get a boundary conditions. They are very simple, where non-dimensional functions for description velocity, density, and pressure. Substitution this parameter u, rho, p in the equation of motion gives 3 equations for these 3 function. And with initial conditions, you can see these conditions here. Integrate them from unity to 0, we obtain the solution for this formula. The picture of this solution you can see here. This is behavior of the pressure. This is behavior of velocity of particles, and this is behavior of density. All of them, after jump, decreases between the jump and the points of explosion. This problem was solved not only Taylor, but our academician Sedov solved the problem analytically in 1946, some before than Taylor solution. And in this case, we can obtain this parameter k, which can be found in the previous way. That's all. Thank you very much. Here you can see strong explosions. This is the zone of explosion, and this is front of shock wave.